then you go to field parameters, and then you start filling the information for each field. So for each field here, you have to specify what are the climate data file, and then you can go to the data files you prepare in advance, and then you can call one of those climate data. I'll call one, for example, here, and then this data will be uploaded into the dialog, and then after that you go to the irrigation. But before I go to the irrigation, there is here in the climate data 3 other options. You should consider the type of radiation you have. If you have total radiation, then you have to say, I have here use the total radiation. The first option, use total radiation from climate data. If you have total radiation and net radiation available, you can take the box number 2. Or if you don't have net radiation and total radiation, but you have sunshine hours, you take the box of use the radiation from sunshine hours. This is in case if you are in an area where you cannot measure radiation, but the sunshine hours is available from the internet anywhere. The model can calculate the total radiation and net radiation from the sunshine hours based on FAO Irrigation and Drainage paper number 56 of 1989. But if you have the total and net radiation, that will be better, that will be more accurate than you calculate total and net radiation from sunshine hours. But if you have only total radiation, the model will calculate the net radiation from the total radiation. So that's in connection with the climate data. We calculate the evapotranspiration data, evapotranspiration rates from different methods. The first method commonly used is the FAO Irrigation Drainage paper number 56 of 1998 by Allen et al. And for that, actually, we the required climate data that we specified. This is based on Penman-Monteith's equation, and I will explain that from the PowerPoint. So this is really where we are. If we have several fields, you can specify them as here, and after that, we have to look at all those processes the model is going to simulate. So the first thing that we're talking about is evapotranspiration, and then we'll talk about plant water uptake, water and solid transport, leaching, soil nitrogen dynamics, soil temperature, drainage and groundwater level, crop yield, water use relation, crop rotation, and also the model can run with 20 multiple fields or separate treatments. Yeah, evapotranspiration here, the formula that widely used because it's simpler, it doesn't require the canopy resistance to evaporation, is the one by 1998 of the FAO, and this is the formula where we calculate the reference evapotranspiration of green grass well watered at optimum conditions, and we calculate the reference evapotranspiration of that green grass, and then we multiply that by 2 coefficients. One is coefficient related to bare soil evaporation. The other coefficient is related to transpiration. The total of those 2 coefficients are called crop coefficient, or KC. If you multiply the KC by reference evapotranspiration, you will get the crop evapotranspiration, ETC. For here, we don't need anything related to canopy resistance to evaporation, because it is assumed to be 70 meter per second as average seasonal value by FAO. The other thing which is more accurate, of course, is to use Penman-Monteith's original formula of 1965, but you will require here to have a data related to the stomata resistance of the crops, and this can be measured or can be calculated. In the model, we can calculate the stomata conductance from Jarvis model, and that would require the vapor pressure deficit and the relative effect of temperature, and also relative effect of water, and the relative effect of the photosynthesis radiation and its effect on the stomata. And then we can calculate the stomata conductance. The second method we use is that we we realized that some time ago that when the plant is stressed, it would release a hormone from the roots, and it's called abscisic acid, or ABA, and that hormone travels from the roots to the stem, and then from the stem to the leaves, and it goes to the stomata, would reduce the conductance and increase the resistance to minimize water losses through the transpiration. And we use that hormone as indication of the conductance. There is a relation between the hormone concentration in the leaves and the conductance of the canopy, or the resistance of the canopy. And we use that value in the Penman Montes, the original formula. And we are using Tardieu model, where we need two things: the abscisic acid concentration and the leaf water potential measured. From these two parameters, we can calculate the stomata conductance, and then we put it back into the Penman Montes equation to calculate the reference evapotranspiration ET node. Another process in the model is the water uptake in presence of salts in particular, and the actual water uptake S, it depends on a potential water uptake, S max, and also depends on the osmotic potential, pi, and also the water availability, or water potential, H. So we have here pi 50, also another parameter, which means that the osmotic potential related to concentration of salts at which the actual water uptake is reduced to 50% of the maximum uptake. So this parameter would actually be used to indicate the 50% threshold as a reduction from potential to actual uptake. Lambda here is a parameter related to the root distributions in the soil. So the soil S max, or the maximum or a potential water uptake by plant roots, is the reference evapotranspiration multiplied by crop coefficient related to transpiration, or KCB. In the model, we also calculate crop yield, and that's a relative yield. And that's very simple formula. We take the sum of the actual water uptake divided by the sum of potential water uptake in the season, and with the relative yield. The actual yield, we multiply the relative yield by the maximum yield obtained or observed in the region. And that's actually is not a very accurate estimate of the yield, but it is useful for running scenarios for 100 years or in relation with climate change. But there is another way that we calculate the dry matter and yield more accurately, and we'll explain that in a minute. The model also calculates the leaching requirement, especially if you are using saline water, which is the concentration of the irrigation water divided by the concentration of the drainage water, or the salinity of the average salinity of the root zone, in case if you don't have the drainage system. In order to calculate the dry matter and yield more accurately, we use the formula that would make sense for those who are working with photosynthesis and some stress factors. What we actually use here is that we use the photosynthesis efficiency multiplied by radiation, multiplied by stress factors related to temperature and transpiration, the presence or availability of nitrogen in the leaves. And this formula will give us the assimilation rate per unit area. But we take from that what's lost through the respiration losses by the plant, and we deduct that, and then we get the net dry matter or net biomass accumulation. So the assimilation here is this is the formula, and actually we use the solar radiation leaf area index and a factor here to calculate the radiation input, and also the radiation should be in megajoule per meter square per day, and the leaf area index need also to be measured or estimated or obtained from literature. But also the plant would have an optimum temperature for grow, and usually the plant would grow between top temperature 1 to top temperature 2. In optimum condition, really this is the best for the crop to grow. if the temperature is cold or low, and then you don't have much growth, and this usually the winter dormancy for most of the crops in Europe, where you have the winter time where plants don't grow because temperature is low. But also when the temperature is too high, also the plants, they get dry and they wilt, and then the growth goes down. So there is optimum range of temperature where the plant can grow, and that's also expressed in the model and taken into consideration when talking about the dry matter. Another thing in the model is the nitrogen balance, and we look at the whole soil nitrogen cycle, and here the nitrogen cycle we use chemical fertilizers added, and also we look at the manure and everything really related to the reactions in the soil and the mineralization, immobilization by microbes, and also nitrification and denitrification of nitrate to nitrous gas, and also the leaching of nitrate from the land to the drains or to the rivers, and also we look at the plant water uptake. So that's very much the nitrogen cycle, and every step of this actually is documented in the paper related to the SALTMED model, and also in the user's guide. In the user's guide also you will have the equations that would describe each of these processes. We have in terms of irrigation, we have furrow irrigation system, we have basin irrigation in the model, where you actually flood the whole land, and also you have furrow irrigation systems where the water would go in furrows, and the plants would go over ridges, as you see those ridges here. And the model also would allow the use of sprinkler irrigation system, and also center pivot system, as well as drip irrigation system. And these are the type really of irrigation systems that included, and I will go through the manual of the model as well to do that. But before I go that, maybe I should go back to the model.